Hi everyone, we're going to look at some 3.0 level learning targets for Unit 6, which was our rational unit. Um, I'm not going to go through every question on this page, but I will go through both of these at the top and then one from each of the remaining learning targets. I do know this unit was a little bit trickier for us, so feel free to pause the video, go back, maybe play it a little bit slower if you need to as well. So for the first learning target, we are solving a rational equation, and then we also want to determine if any of our solutions are extraneous. So I'm going to start with the one on the left. And how I want to approach this is I want to get rid of denominators. So I want to see what denominators I currently have. In this one, I only have one, which does make it a little bit easier because I know if I multiply this first fraction by my denominator, that x plus 1, those would cancel and my denominator would go away. So that's what I want to do, but if I multiply that to my first term, I have to multiply this middle term also by x plus 1 and the 10 by x plus 1. So everything is going to get multiplied by x plus 1. So here, my denominator will cancel. So 30 is all I have for my first term. If I'm multiplying x times x plus 1, I'm going to distribute that in. So x times x would be x squared, and then x times a positive 1 is a positive 1x, or just positive x. Then I have my equal sign, and then I'm also going to distribute the 10 in. So 10 times x and 10 times 1. Now that my denominator is gone, this is a quadratic because I have x squared. I want to get everything to one side of my equal sign and factor my quadratic. I like to move everything wherever x squared is because this x squared is already positive, and so I'm going to move both of these terms to this side. So to do that, I'm going to subtract 10x, and I have to subtract it from its like term, so the other x. These would go away. And then to save some space here, I'm going to subtract the 10 in this step as well, and then subtract the 10 from its like term. I'm going to put it in standard form, so my x squared is going to come out in front. Then I have x minus 10x, which would be negative 9x, and 30 minus 10 is 20. And there's nothing left on the right-hand side. So here I want to factor this. I want to find numbers that multiply to positive 20 that add up to negative 9. So you could go ahead and make a t-chart on the side. Whatever multiplies to 20 adds up to negative 9. I'm not going to do it to save some time in the video, but if you wanted to pause the video and make the t-chart, you could. Our factored form will be x minus 4 and x minus 5. Negative 4 and negative 5 are the two values that I would want from my table. And then when I set each of them equal to 0, I would get x equals positive 4 and x equals positive 5. Before I circle my answers, I do want to double check to see if either of those or both of those are extraneous. What I'm looking for is if I plug it into my denominator, I cannot have 0 in my denominator. We cannot divide by 0. So if I plug in 4, 4 plus 1 is 5. 30 divided by 5, that is okay to do. So 4 works. If I plug in 5, 5 plus 1 is 6. 30 divided by 6, that works. And so actually both of these are solutions. I have no extraneous solutions for this problem. I'm also going to do the one on the right to show a couple similarities and differences. So for this one, I have another equation. I noticed that I have multiple denominators this time. The one that we previously did only had one denominator. These did not have denominators other than an invisible 1. Here, though, I have x plus 4, I have 2, and then I have this, which, if I factor it, would become 2 times x plus 4. If I distribute that 2 in, I get that 2x plus 8. And so this shows me that these two denominators merge into this one. So what I want to do is I am going to multiply every single fraction by this 2 times x plus 4. So I'm going to do it to this fraction, I'm going to do it to this fraction, and the first one. So every single term gets multiplied by that denominator. As a side note, if this last term did not have a denominator and it was just the 2x, I would still multiply every term by the 2 times x plus 4 because those are my two denominators here. So I'm going to cross off what would cancel. If I have x plus 4 in the denominator, this x plus 4 would be in the numerator. Those will cancel, so I'm just multiplying 2 times x. Here, my 2 will cancel out the 2 in my denominator. And then for this last term, everything's going to cancel. The 2's will cancel and the x plus 4's. So I'm going to cross off everything so I don't get confused. So here I have x times 2, which is just 2x. Then I have x times x plus 4, so I'm going to distribute that in, x squared plus 4x. And then I have 2x and nothing's being multiplied to it because it canceled out my denominator. So from here, I can combine some like terms. So I have x squared plus 6x equals 2x because I combined 2x and 4x. And then I can subtract this 2x from both sides. So I have x squared plus 4x equals 0. I can still solve this. It's a different type of factoring. Because there's only two terms, I want to look at what they have in common. Well, they both have an x, so I can factor out an x out in front, and then inside my parentheses would be x plus 4. Because it's still equal to 0, I can take each part and set it equal to 0. So this x would be set equal to 0, which would give me x equals 0. X plus 4 gets set equal to 0. I would subtract 4 on both sides, and I get x equals negative 4. So those are my two solutions, but I do want to double check to see if they are extraneous or not. So if I take 0 and I plug it in here, 0 plus 4 is 4. 0 divided by 4 would give me 0, so that works. And then if I plug in 0 over here, I get 8 in my denominator. So that one's okay. If I plug in negative 4 plus 4 is 0. Negative 4 divided by 0, I cannot divide by 0. So because negative 4 would produce a denominator of 0, that one is extraneous. So I'm going to make a little note. And so my only solution for this one is x equals 0. So I will leave the bottom two for this learning target for you to do. So we're going to move on to 6.3.2. I'm just going to slide this up a little bit here. And we're going to look at identifying our asymptotes and our domain and range for this rational. So the first thing I want to do is I want to factor what I can. My numerator I cannot factor, so I'm going to keep that the same. My denominator, I want to think of numbers that multiply to negative 14 that also add up to positive 5. That would be a positive 7 and a negative 2, so I can write that in factored form. So from here, I can see that my x plus 7 would cancel each other out. I'm going to make a little note. When that happens, that creates a hole. So I actually have a hole at x equals negative 7. The part that's left over in my denominator is where my vertical asymptote comes from. So I'm going to make a little note there so that when I do this part, it helps. So my vertical asymptote is going to be x equals positive 2, because if I take x minus 2 and I set it equal to 0, I would get x equals positive 2. My horizontal asymptote is tricky. For my horizontal asymptote, I want to look at my original equation and the degree of both the numerator and the denominator. My degree is my largest exponent. So the degree in my numerator is an invisible 1, and the degree in my denominator is 2. Since the degree in my denominator is bigger, I have a horizontal asymptote at y equals 0. Let's make a little note down here. If the degree in the numerator is bigger, that means we actually have no horizontal asymptote, and we would just say that there's none. If the degree in our numerator equals the same degree as the one in our denominator, then we look at our leading coefficient divided by our leading coefficient. And our horizontal asymptote is at y equals whatever that fraction will give us. And then the third scenario is the one that we did here, where if the degree in our denominator is bigger, it automatically is at y equals 0. So then for our domain and range, we want to use the information we previously found. For our domain, x cannot be the value of the vertical asymptote, so x cannot be positive 2. I'm also going to include -7 because I have a hole at an x value of -7, so I'm going to include that as a value that is not a part of our domain because it's removed, it's missing. And then for our range, we have y cannot be 0 because that's where our horizontal asymptote is. So if we can find our asymptotes first, that'll really help us with our domain and range. We have one more learning target on the back. So we're going to look at the one on the right-hand side. So here we have in an electric current or circuit, the current varies inversely, let's circle that, as the resistance. So the current is 40 amps when the resistance is 12 ohms, and the current, or we want to find the current when the resistance is 20 ohms. So here I'm going to start by setting this up. So the current varies inversely, so the current equals, and since it's varying inversely, I know it's going to be a fraction with some number in our numerator, and we typically have used K. And it varies inversely as the resistance. So resistance is going to go in our denominator, and I'm just going to use R for resistance. I want to plug in the values that I know, and I know the current is 40 when the resistance is 12. So those go together. So when the current is 40, my resistance is 12, and I can solve this for K. So to solve for K, I'm going to multiply both sides by 12 to cancel out my denominator, and we get 480 equals K. Once we do that, we can write our equation. So we know that our current is equal to 480 divided by the resistance. This is the formula that I want to use to actually answer the question. And the question is asking us to find the current when the resistance is 20. So using this, now that we know the resistance is 20, I can plug 20 into R. So I have 480 divided by 20. And then when I divide that out, I get my current is 24 amps. Sorry, that's a little close to the bottom there. And that would be my final answer.